So we're going to start our paper session with a paper which comes from Sheffield. The main author is Javier Dominguez Caballero, and the co-authors are John Stammersa and James Moore. The paper is entitled Development and Testing of a Combined Machine and Process Health Monitoring System. The group in Sheffield, they're really renowned for their machining research, so I'm really looking forward to see this presentation.
Hi, I'm Javier Alejandro Dominguez Caballero, and this is James Moore, and in this presentation we're going to talk about our research on the development and testing of a combined machine and process health monitoring system. Throughout this presentation we're going to talk about the background of this research, the experimental setup and method that we used, the analysis techniques, the results we had, and the conclusions we found, and the future work or next steps of this work. Now, there's plenty of evidence in academic literature about the analysis of sensor signals in a way that you can find different issues in components, cutting tools, and machine tools. Now, by identifying these issues in process, we can first limit further damage to the component or the machine tool, as well as prevent any additional damage to other components that were manufactured with the same issue. Now, there are commercially available systems in the market, but most of them often rely on static limits and they monitor single signals in isolation. Therefore, the objective of this research was to investigate advanced signal processing techniques and analysis techniques for a machine and process health monitoring system that utilizes a consolidated suite of sensors and machine tool, mainly to gauge the quality of the machining operation whilst the component is being cut, as well as the machine tool's performance. Now, the monitoring system that we used consisted of three main sensor systems. The first one was a 3-axial accelerometer in the spindle of the machine. The second was another 3-axial accelerometer in the test bed. And finally, a power monitoring kit to get some power signal from the machine spindle. We acquired all the signal through National Instruments equipment, as well as controller data through MT Connect. And the experimental work, the machining trials, were done on a 5-axis DMG Mori CNC machine, where we machined 9 blocks of titanium using carbide insets. To gauge the health of the machine tool, we designed 2 fingerprint routines. In the first one, isolated linear moves were done where the spindle was located in the home position, then moved to each extreme of travel of each axis, and then returned to home. And this was done at 8,000, 40,000, and 80,000 millimeters per minute. The other routine we designed was a simple spindle rotation, where the spindle would be located at home location and spin at 20, 4,500, 9,000, 13,500, and 80,000 RPMs. This video shows an example of the first fingerprint routine, which is the isolated linear axis moves. To ensure that the tests were all comparable, mainly for the baselines, we used a calibration tool, as you can see in the screen. For the machining operation or the machining trials, we did shoulder milling around the 9 titanium test vehicles using the parameters on the screen. This allowed 10 layers of material to be cut for each test vehicle. This video shows an example of this machining operation around the test pieces. The failure moves that we simulated on the machine tool included a heavy tool, an unbalanced tool, a cold run that was done first thing in the morning, a warm-up run which was done straight after the warm-up of the routine of the machine tool, and the feed rate adjusted failure mode, which was a marginal reduction of feed rate and spindle speed override. For the machining trials, we simulated surface cracks by drilling small bores into the test piece before machining. We misaligned the part so that we will rotate the test bed to those degrees on the screen. And we simulated a worn tool by using a tool that was previously used in another test vehicle. The fingerprint routines were repeated 16 times in the layout shown in the screen. And for the machining trials, we machined, as we mentioned before, 9 test vehicles as well in the layout shown in the screen.
So to simplify the analysis, we had to segment the signal data that we'd recorded. So for example, we've got the individual axis motions here. So this includes the X, Y and Z motion repeated at the 3 different speeds. So what we had to do was we had to segment each of those motions out from the recording, so we ended up with 9 individual signals. And this is the example in the machining operations. We segmented each of the machining passes out, so we ended up with 4 different segments from each signal that had been recorded. We then conducted a number of different analysis techniques in a bit of an exploratory fashion. The first batch was time domain analysis, and we were looking at the kurtosis, the RMS and the signal mean of each of the signals. We did frequency domain analysis, including fast Fourier transform, and from that we were able to identify the most dominant frequencies in each of those. And then we also conducted time frequency domain analysis, including spectral entropy, as well as continuous wavelet transform. So I'm just going to give a brief overview of the results. There were too many to go through in any detail. So first of all, the kurtosis, we didn't have much luck. We couldn't find any correlation with the simulated defects or faults in either the machining or the fingerprint routines. RMS, we were actually able to identify a drop in the RMS values with the spindle speed override applied during spindle rotation fingerprint routines, but we weren't able to find anything in the machining trials. Similarly, for the signal mean, we found the drop in the RMS with the spindle speed override applied for the spindle rotation routine, but again, nothing for the machining trials. And for the frequency domain results, we were able to find changes in the dominant frequencies across all of the different failure modes. But again, nothing for the machining trials. So we moved on to the time frequency domain analysis. So firstly, the spectral entropy. You can see here there are 2 obvious drops that we identified in the spindle accelerometer signal. And this corresponded with the points at which the milling head passed over the bores, but we weren't able to find any differences for any of the misalignment runs or the worn tools. We then moved on to continuous wavelet transform, producing these scalograms that you can see in the bottom right. They're very useful for illustrating how the frequency components change throughout time. However, it is quite difficult to notice any subtle changes by eye. So here I'm going to change from one of the baseline runs across to one of the feed rate override runs. And you can see, although there is a change, it is quite minimal, so difficult to discern by eye.
As mentioned, it was difficult to see any differences in the scalograms from a baseline test to a defect mode. Therefore, we designed a comparative technique which consisted of taking a number of these scalograms and concatenate them into a single matrix of 3 dimensions. This matrix was then used to calculate an average of the signal and calculate the standard deviation. Then, we used one of the test signals, one of the failure modes, and subtracted the average from the baselines to get an output signal, which was then filtered using the standard deviation to get a resulting image. Here you can see an example of how we used a number of baselines, as I mentioned, to create an average, which was then subtracted from a test signal, in this case a baseline, to get the resulting signal. As you can imagine, being a baseline, we expected to see very little signal elements. If we then use failure mode, in this case a feed rate override, we can see in the resulting scaleogram the signal elements that are highlighted by this defect mode. Similarly, with the machining trials, as you can see, here a failure mode, the failure mode of surface cracks with the bores, you can see in the resulting image how these bores are quite clear.
So, in conclusion, we're able to design and test a monitoring system that combines both machine health and process health through fingerprint routines and machining trials. We found that the majority of single quantity, time and frequency domain features that we tested were unsuccessful. But we did find that time frequency domain analysis, in this case spectral entropy and continuous wavelet transform, showed much better correlations to the induced failure modes than we found with single quantity values. We also were able to design a comparative continuous wavelet transform analysis technique which was able to filter and highlight any signal elements that were related to the induced failure modes. So, our future work. The comparative technique showed very good potential, and we believe that this could be used as a feature extraction technique for further analysis. The scalograms that are produced by the CWT could be analysed by machine learning techniques, including deep learning and classical machine learning. We could also use classical machine learning on the single quantity value time domain features, which we believe may help improve detection capability. We have actually already conducted some testing on this future work, and we're planning on getting this published in the Journal of Engineering Manufacture special issue on machining science at some point next year. The further machining trials that we conducted, they had streamlined fingerprint routines, streamlined machining operations and simulated failure modes, and basically that allowed us to gain much higher repeats to allow for the training and testing of machine learning techniques. And this included CNN fault classification, using custom-made networks and also transfer learning of pre-trained networks, and also classical machine learning classification techniques, including k-nearest neighbour, naive Bayes and classification trees. And we've been able to show quite good success with all of these. So we just wanted to thank the Catapult, High Value Manufacturing Catapult, for funding this research, and also thank you all for listening. Please let us know if you have any questions. Thank you.
So thank you, Javier, John, and James for sending this presentation, for sending this article. We are now going to get live question and answers with the authors in Sheffield. So, hello to Sheffield. Can you hear us?
Yeah, we can hear you. Yeah, hello, France.
Thanks for joining us. Thanks for being live here on the stream in this session of the CIRPe Global Web Conference. Thanks for the presentation, and we will have 3 to 4 minutes to have a discussion with you. The first thing that I'd like to discuss with you is about machine learning. You were revealing a lot of potential about these different methods in different domains that you tried out on your experimental data. What do you think is it going towards? How difficult will that be to find more applications of that in this domain?
So I believe with the, in terms of like the single quantity values, the feature extraction, it's quite difficult to notice any particular trends, as we showed by examining those in isolation. However, with the work that we've conducted since this research, we've actually been able to show that by running it through machine learning techniques, we're able to improve the detectability of faults substantially. We think that's a really good way forward with single quantity values.
Okay, thank you. So that brings me to the next question I'd like to state. It is about the implementation. So right now it's in, let's say, it's in a research stage right now, and it's you need a lot of trained, skilled resources in order to get that running. Can you tell us something about the prospective usage in more industrial environments? How much effort will there be left? How easy would that be to use and to implement? Can you comment on that?
Yes, of course. Well, as we mentioned in part of the presentation, there are commercial systems that try to do a similar thing, but the problem with those is they do it in a very somewhat simplistic way. I think for this, there are many options that this can translate into an application in industrial environment. For instance, to look on a combination of techniques rather than just a single way of detecting errors. Maybe have a different machine learning algorithms working parallel or with other systems like we discussed there at the end with deep learning to do a detection and then classification, that sort of thing. So I think that's potentially the way of moving this to a more complex scenario like industry.
Okay. Thank you very much for answering these questions. Thank you very much for doing the presentation and the article. So we're going to end this paper slot right now. Thank you. Goodbye to Sheffield.
Thank you
very much.
Bye.